Here we have an infinitely large cone made of an infinitely elastic material. We'll assume there's a tiny pinhole at the tip of the cone, but no other cuts or holes are allowed to be made. Is it possible to flip the cone over into this downward-facing cone? Well, yes, of course. One way is to simply rotate the cone 180 degrees over a horizontal axis. Another way is to flatten the cone into a plane, and then form it back into a cone. However, both of these processes involve making part of the surface horizontal at some point. Is it possible to accomplish our original goal without having any part of the surface horizontal at any point in the process? Surprisingly, the answer is yes. Before we explain how this is done, I'll quickly show the whole process in action. To make things clear, we'll add stripes corresponding to the vertical height of the surface. These stripes make clear the location of any bowls, domes, and saddle points. Bowls and domes appear in the bird's eye view as concentric circles, and saddle points appear as a cross. If our cone eversion is successful, we shouldn't see any of these features during the process. So, without further ado, sit back and enjoy the full eversion sequence. Okay, so what just happened? The first steps were fairly simple. We compressed the infinite cone into a tapered ring, using the pinhole at the tip. The ring is then vertically scaled to make the slope more gentle. The last steps are the same, but in reverse. To better understand the main part of the eversion, we'll transform the world into our theta space. During this transformation, any horizontal surfaces will stay horizontal. Notice that each radial slice of the surface is a straight line segment, so the shape of the surface is entirely determined by the height g of the middle point and the slope h of the corresponding segment. If the strip is narrow enough, then we can ensure that no part of the surface is horizontal by preventing h and the derivative of g from hitting 0 simultaneously. Now we've reduced the problem to continuously transforming this graph into this graph, without allowing h to hit 0 at a stationary point of g. Since the horizontal axis is theta, recall that the left and right endpoints must always have the same value. I encourage you to pause now and try this for yourself. Here's the solution I'm using, taken from the paper linked in the description. I've marked the stationary points of g and the zeros of h to make it clear that they never collide. It's time to put everything together. Here we show all 4 perspectives we've discussed so far: the 3D view, the bird's eye view, the coordinate view, and the abstract view. I encourage you to sit back, relax, and admire the beauty of this amazingly non-intuitive result.